All right, so we're looking at another demonstration of how we might be able to take a look at how energy moves through an earthquake. Here, I have just a 6-inch piece of 2x4. A small outlet has been put onto this, a screw with an outlet, or an eye, and then just 2 or 3 rubber bands that have been linked together and tied to that eyelet. So on the front and back side, there is sandpaper. You can put different grades of sandpaper. It would change the results of this project. But essentially what we're going to do is the block is going to be dragged over a semi-rough surface. We don't want it to be really smooth. We don't want it to be really rough. And what we're going to do is we're going to measure how much the block moves in 1 centimeter increments. And what I mean by that, I am going to latch onto the end of my rubber band, and I'm going to record where my rubber band is prior to any type of stretch. So here I'm at 28 centimeters. My block is currently at, I'm going to move this actually, my block is at 0. I'm going to revise this. My rubber band is at 12 centimeters. And what I'm going to do is I'm going to pull the block 1 centimeter at a time. So if I'm increasing by equal increments, and I'm waiting to see when the block moves. If I keep going, I'm going to speed this up a little bit. I'm at 30 centimeters. I get my first movement here. So my rubber band stretched from 12 all the way to 33 centimeters, which incurred a 7.5 centimeter movement in my block. I would record this onto a data table, 1 centimeter at a time, where my block was located. So if I keep going now, looking for a second movement, I was able to move to 42 centimeters, and my block moved an additional 2.5 centimeters. So I would record this, and what I can do is I can create a graph, and I would go all the way to 100 centimeters. I can create a graph to show me what the block or what the energy might have been looking like as it moved through the system. So if we're going to talk about the energy, well, how is energy being represented? Well, first, we have the friction from the sandpaper, so there is a force resisting any energy or any pull that I put on the rubber band. When the block moves, we have kinetic energy, which is the energy of motion. When I stretch the rubber band, I'm providing the energy for potential energy or elastic energy. A rubber band stretches because it is elastic. That's where we get that elastic energy from. Think of elastic energy as anything that could stretch or anything that could bend. As long as it returns back to its original shape, you can put in elastic energy. So when I bend this, I'm putting energy into the stick in the form of elastic energy. Think of it like a battery. It's being stored up. When I let go of the stick, that elastic energy is released in motion, so I have kinetic energy. It just transfers from potential to kinetic. So as the block is being pulled and the sandpaper is providing friction and resistance, I'm putting potential energy into the rubber band. Eventually, the potential energy in the rubber band is going to overcome the friction of the block, and the block's going to have to shift. So we transfer energy from the elastic into movement, which is the kinetic energy. So let's take a look at what that would look like with an LOL diagram. First thing, the reason it's called an LOL diagram, I've got 2 graphs set up with a circle in the middle, so it looks like the LOL text. But the center 0, or the center circle, is going to be where I label my system. In our instance, I've got a block and a rubber band. So we're going to track how the energy moved from the block and into the rubber, from the rubber band into the block. So if we look here, I've got potential energy and kinetic energy, and I've color-coded the 2. At the very beginning, I was putting potential energy into the rubber band as that rubber band stretched. So before that block moved, all of our energy was built up into that rubber band. So I'm just going to put a graph with all the energy in the rubber band. And I'm going to say that 100% of our energy is in the rubber band because the block has not yet moved. So we have 0 kinetic energy. 0%. Now, after or during the movement of that block, my energy has to change. All my energy is in elastic energy, but when we start to move, my elastic energy decreases and gives that energy to the energy of motion. So if I come over here, my kinetic energy is going to start to rise. And I'm going to say it goes about here. And I can really create any value I want for this. Let's say that I have 60%. So 60% of my elastic energy went into moving that block. Well, that means I still have 40% of the energy left in the rubber band. Well, how could that be? Well, after I moved the block, after it shifted, the rubber band is still taut. It's still tense, which means that there's still some energy in that rubber band, just not enough energy to overcome the friction. So I haven't transferred all of the energy, just some of it. So here I might just have 40% of that left over. An important part is that my energy before has to be equal to my energy after. That is the law of conservation of energy. And that law states that energy can be transferred. I transfer from potential to kinetic, but I cannot create or destroy energy. I can't just suddenly have an energy loss. It has to go somewhere. And I can't just suddenly put in energy. It has to come from somewhere. So whatever energy I start with, I have to end with. So if I have 100% here, I have to have equal amounts, 40 and 60%, which would also give me 100%. And this demonstrates how an earthquake might move. We have the friction between two plates. We have the energy that builds up as those plates are pushed and they're stretched. And then eventually that potential energy, that elastic energy builds up and it has to shift. Once that shift happens or that block moves is when we incur the earthquake. How much it moves is what gives us either a large or a small earthquake.